We're live. We're live. Okay. So, we're going to learn a bunch of stuff today. And it's all about polynomial functions of higher degree and the real zeros of polynomial functions. So, at the end of this lesson, we will be able to use transformations to sketch graphs. We'll use the leading coefficient test to determine end behavior. I really don't like that line target because they give you a fancy name in place of just using your brain, right? Anyhow, find and use zeros of polynomials as sketching aids. This is important. Use long division to divide polynomials by other polynomials. We just did that. We just did that. All right. And there's some other stuff. There's some other stuff. But first, let's look at, I want to look at a few different. So here's what we're going to do. We're going to consider all parent functions with even degree or order. Okay? So I want us to build a table alongside graph. Who needs graph paper?
I do.
Okay, let's do graph paper and tables. So, here you go, Kelvin. Here you go, Logan. So, on your graph paper, right next to it, make sure the people behind you, Henry, you have one. This is the cool people row, right?
Oh, yeah.
No, not this column. Okay, so everybody in this column gets a sheet, please. Is there going to be enough there, Hannah? It doesn't look like it. All right. So, here's what we're going to do. We're going to build a table next to the first of your graphs. And you're going to have 4 columns on the table. You're going to have your independent variable, which we are going to call x. And then we are going to have 3 dependent variables. I really should call this f of x, g of x, and h of x, but I wasn't thinking. So on your notes, put f, g, and h of x. G of x and h of x. That way we have, and actually, I'm going to do this one in red, I'm going to do this one in green, and this one in blue. Blue. On French. Alright? So, we should be able to evaluate these graphs pretty easily, yes?
Yes.
I'll go away really far. 9, 4, 1, 0, 1, 4, 9. This is, so 4, that is, let's see, that's green. First of all, 81. Let's see, 16. Yeah, 16. 1, 0, 1, 16, 81. And then to the 6th, ooh, to the 6th. What's 81 times 9? That is 729?
Yeah.
729. Hot diggity. 2 to the 6th. So that's 16 times 4. That's 64. No. That's 64. That's not 64. That's 80.
16 times 4.
No, 16 times 4. 16 times 2, that's 64, yeah. No.
16 times 4 is 64. Yeah.
Wow. So I got that 729 without a problem. I had a problem with 64. Go figure, huh? All right. Math in your head. So, what should I scale this to be? I'm going to scale like so. You guys got 8 by 8 in each quadrant, right?
Yeah.
So we're going to go by 2s on the x-axis so that you can fit all your x's on the x-axis. right? And on the y-axis, let's go by tens. Oh, I'm sorry, by hundreds. So 100, 200, 300, 400, 500, 600, 700, 800, right? So this is 800. That makes this negative 800. All right, so let's graph my red. I'm going to do skinny. Actually, no, I'm going to do regular. I'm going to do that. All right, so when x equals 0, my red function is 0, right? When it's 1 and negative 1, I'm at 1, which is not much higher, right? Remember, that first square up is 100, so, wow. And then when it's 2, I'm at 4, which is not much higher than that. And when it's 3, I'm at 9, which is not much higher than that. And now I'm going to do my skinny line and connect the dots. Like that. Like that. So let's do my green. When x is 0, u is 0. When x is negative 1, positive 1, I'm at a 1 again. 16. Now it's moving up a little bit, right? And then 64 is actually an appreciable amount above the x-axis. And then when I graph that, when I connect the dots there, it's a little goofy on the right-hand side, but graphing is not precise, right? So that's x squared, or x to the fourth, I'm sorry. Now if I graph x to the 6, now I get some action, right? 0, 1, 64, so right there, and then 729, which is right there, and right there. So here we actually got something that looks a little bit like a parabola. But it's not quite a parabola. The only parabola on this graph is which one? The red, the green, or the blue? The red is the only true parabola. Okay? But they all look like parabolas to some extent, right? It's just that bottom is flatter. Or I'm sorry, it's not that it is that it's flatter. Here's what I want to do. This will really illustrate it better. Let's go to our favorite graphing utility. F of x equals x squared. F of x equals x to the fourth, and f of x equals x to the sixth. Okay? Let's go to our home screen. And now I want to change these colors to what we had before. Red, green, and blue. Now, check this out. Now you see the behavior. If you zoom this out really wide, now, let's do this. If we go negative 10, negative 10 to positive 10 on that. And on this one, we'll do negative 10 to 1,000. Okay? it looks a lot like our graphs, right? We got something that looks really flat over here. This is our parabola right here, the red one. The green one is x to the 4th, and then x to the 6th. So there's some weird behavior going on here. First of all, the blue looks flatter in the middle, right? But steeper outside. Well, they all look equally flat in this view, right? So let's scroll in, or zoom in. I want to show you, because it looks like x to the 6 goes up faster, right? But does it always go up faster? Let's go between -1 and 1 here. And then from here we'll go -0.01 to +1. And we'll look at this. Now, remember x squared, right? X squared is actually bigger than x cubed, or x to the 4th, and bigger still than x to the 6th. When does that change? At 1. At 1. All three are equal at 1, right? And that makes sense if we think about it, right? Because the more I multiply a fraction that's less than 1 by itself, it gets smaller and smaller and smaller, right? So anything less than 1, the more I multiply by itself, it gets smaller and smaller. And that's why you're seeing that behavior. So what this does is it effectively flattens the parabola at the vertex and steepens it outside of the vertex. Okay? So that's basically, long story short, what I wanted to get across with my cruddy graphing here. Okay? Now, the same thing we're going to do, these are supposed to be x cubed, x to the 5th, and x to the 7th. We're going to do the same thing with those guys, except we're going to do it on Desmos because I don't want to take 20 minutes to do this again. So the 7th and the 5th and cubed. All right, and I'm going to go to my home screen, and you see a bunch of stuff there, right? Let's go back to my regular I want -100 or -1000 and +1000. Now look, again, my cube function, it looks like it's being stretched out vertically, right, as I go into higher orders. But what do you think is going to happen when I look at x being less than, or the absolute value of x being less than 1? I'm going to be looking at -1 and +1, and we'll do -1, I did it again, -1 and +1. Ooh, I got to zoom in more still. Let's do 0.1 and +0.1. I can't even see it there even. Oh, yeah, I can. Yeah, I can. I'm sorry. So my graph is steeper. Let's try that again. So look at, actually this is a perfect view. Hey Ben, this is actually a perfect view. You see where everything changes again. So it looks, between 0 and 1, it looks like my cubic function is the steepest, right? It gets up to 1, or it's getting up to 1 the fastest. But look at this guy. At 1, my quintic and my septic functions overtake my cubic function. So it's the same thing, the same rules being applied to these as it was applied to my even powers. Okay? So we're going to skip that screen, and we're going to talk about the relationship between factoring and graphing. So consider this function. f of x equals x cubed plus x squared minus 4x minus 4. First of all, see if you can factor that by grouping. Who remembers grouping? Who remembers grouping? Try this. Or factor that, and then common factors to both of those two guys. What's the common factor to this? X squared, right? So that's x squared. This is f of x. Equals x squared times what? X plus 1. And then, what's the common factor here? Let's do negative 4. Negative 4 times what quantity? X plus 1. So now I can rearrange that, right? I got distributive property to distributive property. I can do x squared minus 4 times x plus 1. Can I factor that any further? Why would I ask that question if you couldn't, right? No, not square root. No, it's not perfect square. You're on the right track, but it's not a perfect square. Yes, what do we call this type of polynomial right here? What do I call that type of polynomial? You're right in how it factors, Henry, but what do I call this kind of polynomial? I got a square term, and I'm taking the difference. What do we call that? Difference of squares, yes. And that factors into x minus 2, x plus 2, and then don't forget this guy, x plus 1. And that equals f of x as well. Is that completely factored now? Yeah. Okay. Now, let's consider this burning question right now. Consider where f of x equals 0. Where does it equal 0? Go ahead, Morgan. Okay, why is Morgan saying that 2, negative 2, and 1, or negative 1, are zeros of this function? Why do you think, Wyatt? Yeah, why is she saying that? Right. If x equals 2, this factor turns into 0, right? And 0 times this and times that is going to be 0, right? X equals negative 2. This factor becomes 0. Times this, give you 0, right? X equals negative 1. Same thing, right? So let's consider those values. I got negative 2. I got negative 1. I didn't put enough spaces here. And positive 2. So I want another box in here. Actually, I want another 2 boxes. So here's what I know. First of all, because these are zeros, right? When x equals negative 2, my function equals 0, right? When x equals negative 1, my function equals 0. And when x equals positive 2, my function is 0. So if I'm graphing x to y, or to f of x, I can put a dot. I'm going to do this by 2's again. 4, 6. I can put a dot here. I can put a dot here. And I can put a dot there, right? Because those are the 3 points where f of x equals 0. What about over here? What's it going to be over there? Let me ask you this. You want to erase this. What kind of function is this? Cubic, right? What does the parent function look like? Yeah, look, it's x cubed, which is the snaky thing, right? That's a technical term. Look in your math glossary. Okay, so here's what's going to happen. Now, how many times does x cubed cross the x-axis? Once. Why once? What is the multiplicity of the 1, 0 on x cubed? Do you remember multiplicities? So, factors, what are the factors of x cubed? X times x times x. Those are the factors, right? And what are the solutions associated with those factors? X equals 0, x equals 0, x equals 0. Those are the solutions. So it tells you that f of x equals 0 when x equals 0. The multiplicity of that solution is how many times it comes up as a solution in the function. And how many times does it pop up? 3 times, right? X equals 0, x equals 0, x equals 0. How many times does x equal 2 as a solution to this pop up? Once. How many times does this solution pop up? And how many times does this solution pop up? So how many times is it going to cross? It's going to cross 3 times. Okay? But, back to my original question. X cubed does this, right? It starts way down in the negative land and then goes up to positive land, right? Okay. Now, do I have a negative sign in front of my leading coefficient? So where do you think this is going to start? Do you think it's going to start down here? Or do you think it's going to start up here? Down. It's going to start down. So it's going to start down here. And then it's got to, because a cubic can only cross 3 times. It can only cross the x-axis 3 times. No, let me put it differently. It can cross the x-axis no more than 3 times. It can cross twice. It can cross once, but no more than 3 times. Can it cross less than 1 time? No, because it has to start down here and end up here, right? Okay, so because it crosses 3 times total, what do you think is going to happen here? It's going to go into positive land and then go back down to 0. And now it's in negative land. And it's going to go up. Now, how far up? How far up here and how far down here? I don't know until I actually put some values in. Right? This is going to go down to negative infinity, right? And it's going to go up to positive infinity. All right? Now, remember that leading coefficient test that was our learning target that I said I didn't like? That's the leading coefficient test. My leading coefficient on a cubic, I know what a cubic does. It goes down to the left and up to the right. If it's negative leading coefficient, what's that do to my function? It reflects it about the x-axis, right? And then it becomes this. Okay? If I got something, and that's true with all odd power or odd degree functions, right? All odd degree functions are going to look like this unless they got a negative leading coefficient, and then they do this. Okay? How about even powers? All even powers look like this until I throw a negative in front of the leading coefficient, and then they do this. They turn from smilers into frowners. Okay? Fancy term for leading coefficient test. Okay? These guys, I don't care. I've been able to reason on my own what this graph looks like. Okay? Now, what if this was, I'm going to erase the blue function, and I'm going to do a green function. And let's call g of x equal, I'm going to do this factored already. X minus 1 squared. Now let's do a different number here. Let's do x minus 3 squared. Yeah, and x minus 2. No, not x minus 2. X minus 4. I like that. What do you think this is going to look like? First of all, where are my zeros? 3 and 4, right? So I'm going to have a 0 there and a 0 there. Now, has this got a negative leading coefficient, do you think?
No.
No, because x times x times x is x cubed. It's going to be positive x cubed, right? So it's going to look like this, right? How many times does this cross the x-axis? Twice. How can something that do this only cross twice? Well, it's going to start down and to the left, right? So it's going to start down to the left, and it's going to end up and to the right. But because this has a multiplicity of what? How many times does it come up as a solution? It comes up twice, right? It comes up twice. So instead of this actually going through the x-axis, it's going to touch it and bounce off and then go back up through the other one and off to infinity and beyond. Does that make sense? Okay? So I can gain a lot of information from factors. I can gain information from the factors. What do the factors tell me? Tells me my zeros. It tells me where my graph crosses the x-axis. And I can also, because of the multiplicity, I can tell you what they look like, right? Whether it goes through or whether it just bounces off like a stone on a pond. Right? Okay. Forget what I wanted to get across to you guys here. Factor this guy and sketch the graph. What did I want to, well, is it though? What did I want to get through on this? I gotta look at my notes real quick. What did I want to do here? That looks like an awful function. I had a point to this. I promise you I did. Oh! Yes! I remember my point. Okay, factor this. How much time do we got left? 4 minutes. Can we factor this? Is it factorable?
Yeah. Yes.
Make it so, number 1. Right? I can see that. You're factoring that. Can you factor it? How many people are throwing up the white flag right now? All right. I'm going to give you a hint. Let's do. How many factors does a cubic have? 3. All right, I'm telling you, this is one of the factors. Now can you factor it completely? What's your first step going to be? How? You going to subtract it?
No. We're going to split it up into 2 groups.
What did we do yesterday, kids? So divide. While you divide, I am going to copy up. I don't know. Well, you dividing right now? Get hot. Oh no, I gotta do work. Oh no. So, if you divide this, you should get. What did you get when you divided?
Oh my God, there's no remainder.
Yes.
There's no remainder.
No, there's no remainder. No. What'd you get?
Oh, there's no remainder. But I was so confused.
What'd you get, Henry?
We got turned by subject.
Yeah, you just said that.
3x squared minus 5x minus 12. Can we factor this? Yes, you can. So your job for tomorrow, have this factored, and then try and figure out what your graph might look like. That's your job for tonight. Factor this completely. We've done the first step to factoring, right? With our hints. But can I factor this any further? Look, and then you'll get the answer. Can I factor this any further? Can I factor this any further? Okay, factor that, and then use your factors to figure out what the graph looks like. Right? You can.